Thank you, Vincent, for this introduction. So, indeed, I was in Normandy, one of the pioneers of living soil market gardening. We invented this concept one day around a table. We had the idea to activate a number of technical levers to change our agricultural practices. And what seemed to best correspond to what we were trying to do was this notion of living soil. So, I will try in 20 minutes, which is very short, to explain to you why the soil is truly alive and why, in fact, we must consider it as such. And also why, from the moment we consider it as such, truly as a living being, it greatly changes our agricultural practices. And it also greatly changes the results we have in the field. The energy efficiency, the environmental efficiency, the efficiency. Nutritional, well, that's not really a term, but it doesn't matter. The nutritional result. Why, from the moment we consider the soil as something living, it completely changes our perspective on agriculture and our profession. The first observation we made was quite simple. It's that if we look at nature, in fact, if we have too much water, living things don't develop very well. The living things that interest us, plant production, because in the oceans, there's a lot of life, but there are no lettuces growing in the ocean. So if there is too much water, it doesn't quite align with what we want to do. If it's too cold, it doesn't work either. We know it. We are market gardeners. We have to set up greenhouses to grow summer vegetables that need warmth. If it's too hot, too dry, it doesn't work either. However, if we are within a correct range of temperature and humidity, suddenly, something happens. An absolutely magical thing. Everything grows. Everything starts to grow tremendously. It's a simple observation. We can see it every day. The forest grows, the roadside grows. Everything grows, except there's something very interesting about it, which is that it grows completely on its own. We do nothing. We just have to wait, and it grows. This raises a lot of questions. Especially why, in agriculture, it's not enough to just watch the wheat grow. Why don't we just stay in our chairs, and then the wheat doesn't grow? Why, for example, are we forced to work the soil? Why do we buy 400 horsepower tractors, plows, cultivators, rotary harrows, etc.? What is the real purpose of this practice? Why do we use fertilizers? An oak forest, no one has ever come to apply fertilizer. No one has ever come to work the soil, yet the forest grows very well on its own. Why do we do crop rotations? Today we hear a lot about rotations, how they are supposed to improve the environmental performance of agriculture. We must do rotations. I don't think nature bothers to move the chains every 10 minutes, or every year, or every 2 years, every 5 years, thinking, hey, 1 year I'll plant an apple tree, the next year an oak, because I'm going to do a rotation. There are no rotations in nature. It doesn't work like that. There are ecological evolutions, there are ecological stages, there are forms of evolution, but there are no rotations. So why us should we do rotations? And a whole bunch of other practices. For example, why do we do composting? There aren't people in the forest having fun gathering all the leaves, making a big pile of compost, and putting it back at the base of the trees. It manages itself, it happens on its own. Why does our agriculture pollute? Why does it pollute? If I tell you that the forest and the meadow do not pollute, that they provide clean water, it's not true. 100%? 100%, but at 98% it's true, and it won't surprise nobody. So why all of a sudden are we forced to do all this, resulting in pollution, numerous environmental problems, and high energy consumption, while nature offers us a model that has absolutely nothing to do with it, and it works entirely on its own. Alone, except the problem is, nature doesn't naturally produce wheat or lettuce. So, the next question we asked ourselves was how to grow lettuce, wheat, fruit trees, while best respecting this natural model that grows on its own. That has been our guiding principle. Now, let's talk a little bit about living organisms and ask ourselves the question, is the soil really alive? Because in fact it turned out for us that the problem primarily came from there. Just as we easily consider a wheat plant to be a living being, a lettuce to be a living being, a tree to be a living being, the soil, is it really alive? It doesn't necessarily have an exterior and an interior like a human being or a plant. We have difficulty defining its contours and limits, and we especially struggle to see its activity because in fact, it might be happening over a longer period. And so, we might have a bit of trouble understanding in what way it is alive or not. So, a rather simple thought experiment. Here, in this photo, everything was made by humans. We know how to make that. If we put enough engineers to work with machines, etc., they will manage to make absolutely everything that's in there. On the other hand, if I put you in the forest and ask you to make something that's there, in this image, I ask you to make a leaf. I ask you to make a branch. It makes no sense. You are incapable of making a tree. You cannot take pieces of branches, nail them together, assemble them to make a forest. So we see that there is still fundamentally something extremely different between the living. Since we ourselves, with our technologies, are still today incapable of making it from scratch, whereas in this supermarket, we are capable of manufacturing everything that is there. And for good reason, our technologies, they consist of. So I have listed a number of verbs that are related to our technologies, to our ways of producing things. So to make objects, we nail, we screw, we melt, we paint, we saw, we mill, we turn. We have a whole range of actions like that. On the other hand, nature does not work like that at all. These are actions that have nothing to do with it. If you try to bolt a branch onto a tree trunk for fun, that's not how you make a tree. It doesn't work like that. What I'm trying to tell you is that these are two completely different technologies. So sometimes it's a bit misleading. For example, here we have a board. These are indeed pieces of wood that have been glued, pressed, compressed, but we made it into a board. We didn't make it into something living. Nevertheless, if I take the board and let it rot on the ground, it will become alive again in a sense because it will decompose, it will feed a food chain. But if this board were made of plastic, it wouldn't work. So we indeed have two very different technologies, and this can allow us to ask the question, is the soil actually alive or not? Now, this is something quite well known in the agricultural world. It's that if you take a normal, heavily worked agricultural soil today with quite low organic matter levels, now I say normal because that's the standard today, many agricultural soils are like this. And you put it in water, so it's the photo at the top left. Well, 30 minutes later, it's the photo at the bottom right. They turn into mud. So if you're wondering about the origin of agricultural pollution, don't look much further. You have 90% of the answer in these two photos. Today, agricultural pollution, we hear about chemicals, we hear about all sorts of things, but the primary reason for agricultural pollution is right there. It is there. Now, the one on the right, I also included it. Well, it doesn't quite fit into the order of my presentation, but it's a soil in which I added compost, and we can see that it doesn't work either. So we will also need to question compost. As I was telling you, in nature, no one bothers to make large piles of compost to go and nourish the trees. It happens on its own in a slightly different way. So here I ask you a very simple question. Do you know of a living being that cannot withstand water? A living being that will melt and die as soon as it rains, for example? Find me an example of a living being that absolutely cannot tolerate water. Ah, no, contrary, earthworm. A living being, you put a drop of water on it, it explodes, it starts bleeding heavily, excuse me. But in fact, there isn't one. Obviously, water is extremely connected to life, and all living beings are resistant to water. So the soil then, today our soils are like this. We see this everywhere. Why? What is the deep reason for this? If I take, on the other hand, natural soil types, a prairie soil, and I put it in water, I wait 7 days, not 30 minutes, but 7 days, the clod of earth hasn't moved at all. It hasn't dissolved. We could measure if there have been any diffusions. So, indeed, there is a little bit of material, trace elements, nitrates, etc., that diffuse a bit into the water, but actually very little. A forest soil is exactly the same. Well, here, I couldn't take a nice clod because it's filled with roots, so as soon as you take out the clod, it crumbles a little. Soils, naturally, are also resistant to water. They have the same living property of resisting water. And for good reason, because if they turned into mud with every rain, it would be very complicated for nature to have a structured, aerated soil with biological activity inside, etc. So it's one of the fundamental properties of soils that is common. With living organisms, it is to be resistant to water in a certain way. I won't dwell on it, because in fact, if you really want to understand, that's what we're trying to do in our training sessions. If you really want to understand why soils resist water, it's quite complicated. You need to delve into quantum physics, study a whole bunch of things. These are fairly complex mechanisms, but fundamentally, it can be observed very easily. And that's what we've tried to replicate in our agricultural soils, soils that resist water. And we've conducted a whole range of measurements. And strangely, 98% of the pollution disappears once we regain this property of water resistance, which is very visual and ultimately very simple to understand. And to explain this, we invented a recipe. It's the recipe for pollution. And so we say, to pollute, I make coffee. If you take a coffee bean and put it in water, excuse me, I just got back from Mauritania, I'm a bit sick. There are some strange bacteria. Over there, the soils aren't very lively, and on top of that, there are some somewhat dangerous bacteria in them. If you take a coffee bean and put it in water, well, it doesn't dissolve. Why? Because it is structured. It is structured. Originally, it was alive, even though it was roasted. It retained its structure. However, if you grind it finely and add water, it makes coffee. Why? Because you have actually destroyed the carbon structure of the living thing. And you have extracted everything inside it, all the aromas, etc. And you have made coffee. If you take a clump of soil with a bit of wheat on it, if you add water and put it all through a blender, you do exactly the same thing. You destroy the carbon structure and you make a sort of coffee. Because it's good. The carbon structure of the soil, the organic matter in the soil, which greatly helps with water resilience. There is a very strong link between the carbon matter of living things, which allows resistance to water, structuring water, and creating something stable, despite having recurring rainfall. And so it helps prevent everything that contains life from being washed away into the water, into the groundwater, etc. So this is something we have also understood, that living things are carbon structures, which circulate physiological fluids, such as blood, lymph, tree sap, etc. And within this liquid water, soluble elements circulate, and from the moment we destructure this carbon structure, all the soluble elements escape, and then we get pollution. We have learned in the living soil farming network to recreate this carbon structure. So it's a bit complicated, we can do it in many different ways, but to put it simply, we add a lot of organic matter to the soil. So here on the left, you have a kilo of soil in which we added 10% of freshly crushed branches, which served as food for networks of fungi, bacteria, various insects, and microorganisms. We waited patiently for 6 months, keeping the clod moist, but not waterlogged. And 6 months later, this clod became perfectly resistant to water. I still have it on my farm, by the way. It's been in a container and soaking for 3 or 4 years. There's some grass growing a bit on it. We recreated a living soil with a large part of its properties. Originally, it was a clod of soil with very little organic matter, and that would easily dissolve in water. So we learned to do all that, and we can do it in many different ways. I'm telling you, we can do it with dead organic matter, with cover crops. We can do a whole bunch of things. We learned to do all that, but we learned to biologically rebuild the soils. So what happens in this biological reconstruction of the soils? Who actually does the work? Because it's not us. It's not us who had fun opening each clay strand and wedging organic matter inside. Who naturally does the job in nature? Well, it's that. It's those things. You have here, in the middle, at the bottom, networks of fungal filaments. You should know that every time you put fresh organic matter into the soil, fungi start to consume it. The first thing they do is weave extremely dense networks of various filaments, which are carbon filaments, and they are water resistant, stabilizing the soil, stabilizing the earth. The earthworm indeed does an enormous job, as it is the one that brings organic matter down into the soil, and it is the one that redistributes organic matter in the soil. The roots of plants also inject carbon into the soil. And then you have a whole array of microorganisms, mites, bacteria, a whole bunch of various insects, which, in fact, when we study their diet and ecological cycle, spend their time doing the same thing over and over. It is eating organic matter, spreading it in the soil to build the soil and stabilize the soil. And so they are the ones doing the work. I don't know how to stabilize soil. Just as I don't know how to make a tree in the forest, just as I don't know how to make a leaf, I don't know how to make soil. However, there are biological beings who know how to do it, and it is with them that I must collaborate. And so that's where we begin to understand the living property of soil and how we will be able to work with living soils. Because in fact, it's all these little creatures in the soil that are alive. What we also need to understand is that life is a nanotechnology that organizes everything, from the infinitely small to the macroscopic. You each of your atoms, each of your molecules, your body, your organism has reorganized them, atom by atom, molecule by molecule, to fully construct you. We didn't take large chunks of ground beef and stick them together end to end to remake a muscle. It is truly atom by atom, molecule by molecule, that you have been reconstructed by your own metabolism. And that is a very significant distinction between so-called living and non-living technologies. It's that living organisms reorganize everything, from the infinitely small to the macroscopic. And this is very important to understand because it shows us the complexity of living organisms. And the day we ask ourselves how we are going to maintain a soil, work a soil, build a soil, improve a soil, amend a soil, we must understand that it is an extremely complex nanotechnological organization, and that perhaps it is something that slightly surpasses us. And especially our modern tools for working, the soils are not at all capable of doing this organizational work, from the infinitely small to the infinitely large. So, from the infinitely small, from bacteria to the macroscopic, the roots, the trees, the largest living beings, macroscopic, life spends its time organizing everything. Just like you are organized from the cell to a being that is almost 2 meters tall and nearly 100 kilo. Molecule by molecule, atom by atom, life in the soil organizes the soil, and only it knows how to do it. What is a bit disturbing in this story is that, in fact, the rules governing all of this escape us in many ways. And at some point, we have to learn to work a bit blindly. That is to say, we must understand the main rules, but we must let all these living beings do their work. We must let them work because they do the job much better than we do. I assure you, really much, much better than we do. And we must trust them. In fact, what we need to do is understand their ecology, understand how they function, and how we are going to work with that. What I also want you to understand, which is a bit provocative obviously, is that trying to build soil with this kind of tools, whether it's animal drawn or motorized, with hundreds of horsepower, it doesn't make much difference. Wanting to build, wanting to structure, wanting to organize, wanting to improve soil with these tools, well, it costs. It's exactly the same logic as if you said, I take an apple tree, I will grind it into small pieces, and then I will hope that it will give me apples afterwards. When you've used tools like that, do you think it benefits earthworms? Do you think the networks of fungal filaments, which sometimes extend over hundreds of square meters, find it beneficial? Do you think that, for example, an earthworm, which takes several months to dig a very organized tunnel that allows for water drainage, etc., fulfilling many ecological functions, these tools, in fact, do not adhere to any biological laws, absolutely none. When we do that, I'm telling you, it's not much more sensible than taking a plant, grinding it into pieces, and then thinking, well, I have ground up pieces of apple tree branches, and with a bit of luck, it will give me apples. It doesn't occur to you. The question is, why doesn't it occur to us that the soil is also structured, also organized? Because we understand well that the apple tree, once it's ground into small pieces, simply doesn't function anymore. So why do we persist in grinding the soil, thinking it will continue to function? This is the beginning, this consideration, which is very theoretical. It starts to help us understand why suddenly, when we've worked the soils, we will need fertilizers, we will need to work every year, why we will start to have pollution, and why we will start to have all these problems. So how does it work? In fact, a soil, how much time do I have left? 5 minutes. How does it work? A soil works according to something very, very simple. All living beings have a very, very simple property, which is that they eat. You need two things. First, you need to make sure you don't get put through a grinder, because otherwise it works a lot less well. And you need a second thing, which is to eat. So what does soil eat? The soil always eats the same thing. There can be a few small nuances, but the principle is extremely simple. It's that you have photosynthesis above that makes plants grow. These plants, let's say they contain energy, carbon energy, leaves. If they are dry, they burn wood burns that contains energy. And in nature, what happens to all of this organic matter? Well, it falls back to the ground. Dead roots are in the soil. Leaves in a forest that fall to the ground, they fall to the ground. And so, what is the role of the soil? It is very simple. It's to consume all the organic matter in the soil, to feed on it. And what do they do in the process? They structure the soil, they create the soil, they organize the soil according to their own laws. It's as simple as that. Above the soil, we have plants that produce organic matter through photosynthesis, and below, the soil that consumes, structures, and organizes. It was a gamble we took about 10 years ago, which was to say, if I stop destroying my soil with tools and feed it abundantly at some point, it should start functioning again. And when I plant plants on it, they will grow on their own. Well, I'm telling you, it works. The only question that arises when you're a practitioner is how long it takes, how much organic matter I need to put on the soil. In short, you have to size things appropriately. Because if I give you a ton of rice to eat every day, it won't go down too well. If I give you a single grain of rice to eat every day, it won't go well either. How much do you eat, roughly, every day? Let's say in dry matter, 500 grams and kilo. That's your general range. You don't eat 100 times more, you don't eat 100 times less. There are days when you're a bit indulgent, like during the end of year holidays, you eat more. But that's the general range of your portion. So, the question that arises when we try to think about this ecological cycle is how much the soil eats. Because if you don't respect that, you can't expect the biological activity of the soil to function properly. And so another subsidiary question, if I don't give it enough, what will happen? And if I give it way too much, what will happen? These are very simple questions to which we have responded just like that, and which have allowed us to build functional agricultural soils, in which plants grow on their own. So, to put it simply, it's the soil that feeds the plant, it's what allows the plant to grow, and it's the plant, when it dies, that helps nourish the soil. And even while it's alive, it helps quite a bit in structuring the soil. The problem we have in the agricultural world is that we do this, we have a cycle, and we are constantly removing things from this cycle to feed ourselves. It was also necessary to build our models to quantify what leaves the field, and I tried to establish a sort of ratio to say that we are allowed to take out so much, but no more. We have an ecological cycle at a certain intensity, and we are allowed to take a certain part of it. The problem is that if we take too much, it no longer works. We had to define in our systems what we were allowed to take and what we were obliged to leave. What we understand nonetheless by observing this cycle, which is quite intuitive, is that the more intense this cycle becomes, the more plants we will grow, the more there will be to feed the soil, and perhaps the more we can take for ourselves as well. So, what we are proposing to you, nonetheless, is an agricultural model, and it's important to understand this. It is an agricultural model that seeks to constantly maximize production. The more intense my ecological cycle is, the more opportunity I will have to take from my field without deteriorating my system. This raises big questions, because today there are certain agricultural models that tell us that to produce well, you need to produce less. We say no, to produce well, you need to produce as much as possible. It's not about producing a lot, it's about producing as much as possible, because that's what nature does too. Nature's model is to constantly produce as much as possible, and only produce well. It doesn't make sense to say that a forest produces its trees poorly. You understand this logic well. So, what happens? I'll tell you. The figure is quite simple. In our temperate climates, you need to manage to produce between 20 and 40 tons of dry matter per hectare per year, including straw, leaves, roots, root exudates, to successfully nourish the soil. And if you can't do it, that's what we do in market gardening. Our vegetables can't produce this material, we import it from elsewhere, and that allows us to compensate, and it allows us to keep our soils alive. And so constantly, our systems, what do? They naturally destroy themselves. You yourself, if you stop eating, things will go badly. After a while, you will wither away. And the soil eats, it builds itself by consuming food. And so we must respect this balance of the soil, which is a balance that every living being must also respect to stay alive. He ended up with, at the conclusion of his reasoning, 2 equations. I think I'm going to stop there afterwards. 2 equations, they are very caricatured. There is a lot to criticize, but it still allows us to understand our approach in broad strokes. This is roughly the agricultural model that was proposed to me when I started in market gardening about 10 years ago. I was told you have to work the soil. In the end, the soil, you just need to add a bit of chemistry, a bit of fertilizer for it to grow. The problem is that ecologically, it corresponds to what we call a desert. How do we define a desert? A desert is simply soil that is not capable of growing a plant on its own. And unfortunately, that is indeed the definition of most of our agricultural soils. So if we take a meadow, for example, it grows on its own. If you add a bit of fertilizer, it grows even better. But overall, a meadow is still capable of growing on its own. But most of the agricultural soils we have, if we don't work them every year, if we don't add fertilizer every year, they are incapable of growing a plant properly and healthily. And that is the definition of a desert. It's soil that is not capable of being productive. And the two reasons for this desertification are soil tillage and low biomass production. I've already talked a bit about it. The desertification of these soils leads to a lot of environmental problems that are all actually linked to this thermodynamic equation. It's always the same. We have soils that compact, they are no longer resistant to water. As soon as it rains, they compact. There is no more biological activity, obviously, since there is nothing left to eat. So we cannot expect earthworms to multiply, or fungi to multiply, when they have nothing to eat. We have big debates today about the climate. I would like us to take a closer look at the impact of the presence of plants on the climate. I just returned from Mauritania specifically, and right in the middle of the desert, I met someone who is right in the middle of the desert. You can check it out on Google Maps. It's called Booty Limit. It's 150 kilometers from the capital of Mauritania, Nouakchott. So I met someone who built a very large fence in the middle of the desert. Over 350 hectares, I believe, to prevent animals from coming and eating the plants and trees, because over there the desert is advancing as the animals are constantly eating. The vegetation, so he just put up a very large fence, waited 10 years, and the forest is starting to grow back. And you can see it on Google Maps. There's a green spot right in the middle of Mauritania. It's just because a fence was put up, and when you go to that place, strangely, the weather is much better. Because in fact, the main role of plants is to regulate the climate, to provide shade, to capture the sun's energy. And the plant cover that we should have everywhere in our agricultural systems plays a very important role in climate regulation. So loss of organic matter, low useful water reserve. The richer the soils are in organic matter, the more they can hold water, store water, and notably prevent floods, landslides, etc. Erosion of biodiversity. Now, there would be a lot to say about biodiversity, but fundamentally, the most interesting and important biodiversity is in the soil. It's precisely because we put a lot of food in the soil that you have huge trophic networks that develop in the soil and provide many ecological services. And the deterioration of water quality, obviously, I showed you, by putting clumps of soil in the water. What we propose is another model based on maximizing photosynthesis, maximizing biomass production continuously. We don't necessarily achieve this in all models. For example, in market gardening, we understand well that an 18-day-old radish does a bit less photosynthesis than a 100-year-old oak. That's clear. Photo one is stronger than the other. We agree on that. But nevertheless, we strive towards that. We always strive towards that and try to adhere to these rules. That doesn't mean we always succeed. This will also raise a number of questions for us. Are some of our plants truly suited for sustainable agriculture? Are we going to achieve sustainable agriculture with 18-day-old radishes? As long as it represents a very small part of the French agricultural area, it won't pose too many problems. But, on the other hand, there are crops like wheat, which represent a very large agricultural area. And perhaps we need to question the way we have selected wheat. Does the way we have selected wheat truly allow us to maximize biomass and make the best use of the sun's potential? So the cessation of soil tillage, as I mentioned to you, and overall, if you adhere to these two rules, in one way or another, fertility always returns. And what is fertility? It's a soil on which you plant a plant and it grows, with the caveat that you will need to manage weeds. That is going to be a major debate. Today there is the entire debate about chemistry and herbicides. It's a debate in our technical development about what we will use for weeding, since you understand well, once again, that between the century-old oak and the lettuce, in terms of ecological competition, it's the oak that will win. So, even if we have very fertile soils where plants grow very well, we will still need to have powerful weeding tools. And so it will be up to us to decide which ones are good or not, since, as I showed you, we are not very favorable to using the plow for weeding. And so what tools do we have left for weeding? How will we need to proceed? There you go. Thank you. Vincent, I'll give the microphone back to you.